Good morning. I'm Andrew White, Director of Valve Products with the Lessman Instrument Company. Thank you for taking the time to attend our webinar this morning. Our topic today is improving performance in chromatography by reducing pump slip. This webinar will be recorded and posted to our website for anyone to listen to at a later date. Please enter your questions in the questions section of the menu bar. We'll answer those at the end of the session. I'm pleased to announce the speaker for today's presentation, Megan Sider-Elm. Megan joined Richards Industrials as a global product manager for sanitary products in 2021 to focus on the stainless steel market space. Prior to that, she served as product manager and application engineer for valves in the specialty chemical, refining, and petrochemical industries. She holds a bachelor's degree in chemical engineering from the University of Pittsburgh. Megan, you may begin your presentation.
Thank you, Andrew, and thank you everyone for joining. So yes, today we're going to talk about chromatography, a very important step in the biopharmaceutical and pharma manufacturing process, and some of the issues and how we can address them. So today's topic, we will go through chromatography, a process overview, and this typical equipment used, and then we will focus on pump slip or push-through flow, what it is, how it occurs, and how it really can affect the separations process. And then finally, we will go through how it can be prevented and some of the benefits of the product that we will be highlighting as a solution towards this problem. So just to highlight the initial application of chromatography. So chromatography is a very critical step for purification in biologics. It's a very commonly used process. And basically, it works by using buffers of different pHs that are flown through a column packed with various resins to achieve a level of separation. The more precise and controlled the buffer flow is into the column or the gradient into the column, the more efficient the process will be in increasing the overall yield of the biologics that you are producing. And in order to, if this process is effectively carried out, you will reduce waste as well, because the buffers and product in the column is very expensive to maintain and produce. So ultimately, the goal is to have a very high yield, a very efficient column, and ultimately reduce waste and improve the product coming out of the column. So this is a very simplified schematic of the chromatography process. So typically this starts with several different buffers that are blended as needed through the column, or blended as needed to achieve the desired pH in order to remove various proteins out of the column. So in a application like oligonucleotide production, you're going to be producing various long chains of proteins that will adhere to the resins within this column here. Once these proteins are built and are required to be pulled out of the column and separated, each protein will have a different pH that will cause it to release from the column and be able to be separated and removed for further purification. As you need these buffers, they are blended in real time, and they will vary through the column. So these are blended with use of positive displacement pumps, and the pumps are used to control the flow into the column. As you need different pHs, the pumps are adjusted and then flown into the column. You also want to make sure you want to reduce the amount of pulsations going into the column, because as you have pressure pulsations, this can lead to a disruption of the resin beads and potentially damage the proteins that are being produced. So the key to chromatography is having a really precise gradient elution, and then reducing the amount of disruptions from pulsations into the column. So the first step in this is, like I said, is the various buffers that are used to actually achieve this separation. Typically, these buffers are located above the clean room. So the chromatography step is typically conducted in a clean room, and because buffers are stored in big containers, in order to reserve room in the clean room, they can be stored in levels or floors above the actual clean room, and then pumped down into the room. This reduces space, but it also creates then a head pressure that the buffers will flow then into the pumps. So the pump flow rate will be adjusted as the buffers are needed to mix. but then the head pressure needs to be taken into account. If you don't store buffers above the clean room, typically these are in big vats. So even in small chromatography systems where you don't have large buffers above the clean room, you can still have big tanks that also then produce head pressure. So then the second step is once the buffer meets the desired pH after it is blended with the pumps, it is then pumped into the column. So ideally, this media is flown into the column with as little disruption as possible so it does not affect the protein chains or does not disrupt the resin. All of the resins are very finely packed in a highly engineered way to get the precise surface area required to achieve the separation. As you have pulsations going into the column, you can disrupt the resin matrix and it will affect the overall yield or the separation you get, which affects the amount of proteins or biologics that you are hoping to achieve at the end of the cycle. So as I said, the actual blending process is controlled by typically a positive displacement pump. These work by moving a fixed volume through a series of locks and channels to generate enough head pressure to then flow the fluid out of the system. So this is just a cross-sectional drawing of a very commonly used positive displacement pump, but it's a very typical pump used in this process. So as media flows in, the diaphragms basically act as check valves, generating enough pressure to then flow the media outside of the pump. As the RPMs are increased, you're going to get a higher flow rate and to adjust for the pH desired. So even simplifying the schematic from before a little bit more, you have a pressurized tank or a tank just above the clean room. So a typical one floor above could be anywhere from 7 to 10 feet above the actual clean room, can generate about 3 to 4 psi of just static head pressure due to the weight of the media in the tank. So again, this is mostly done to preserve room in that clean room. The clean rooms are smaller areas and they don't have a lot of room to store multitudes of different types of buffers. So by just moving this above the floor or moving this to the floor above, they are able to save a lot of room. However, you do generate then that head pressure. So like I said, 7 to 10 feet, you're looking at 3 or 4 psi on average. But if you have larger tanks or even higher or stored on higher floors, you can have a significant level of head pressure. And this can be referred to as either elevation pressure or net positive suction head. Ultimately, it is just a higher level of pressure than atmosphere if the pump was just starting at a even pressure. So the higher this tank is stored, the more head pressure is generated, which increases that net positive suction head. And this can cause an issue of push through flow or pump slip, which means since this pump is meant to be starting at standard pressure, the flow or the positive head pressure will push through that pump, filling the chambers and cavities and push through even when the pump is off. So when the pump is at 0 RPM, not operating at all, that positive head pressure is enough to push media through the channels of the pump and continue flowing. So like I said, this is referred to as several different things in industry. Pump slip is very common, push through flow is very common. And what this means is even when the pump is off, there will still always be flow occurring, especially as you have that higher head pressure if you're stored at higher elevations in order to preserve that room. So what does this mean for a chromatography system? So push-through flow overrides the pump's ability to actually do effective control at lower ends of the pump range. Since you have a net positive pressure, the pump cannot operate at those lower pressure levels. If you want to control flow rate at low pressures, the pump does not have the ability to counteract that head pressure. So when the pump is not operating, you will still always have some level of flow going through that pump. And when you look at, a typical cost of buffers is $60 to $70 per liter. I've seen, up to $80 a liter. So they're very expensive buffers that are needed in this process. And depending on the head pressure, I've seen push-through flow can be as high as 30 liters a minute. That would ultimately be dumped to drain while the pump is off and it is not needed going into the system. So it does become quite an issue to be able to control this push-through flow and avoid wasting very valuable buffers, because even a few minutes of uncontrolled pump slip can lead to hundreds of dollars of waste of these buffers that are needed to perform the chromatography process. So how can we prevent this? There are several different ways end users look to prevent pump slip. One of the most common ones is, and most readily thought of, is just to simply put an isolation valve right at the outlet of the pump to turn off the flow once the pump is off. So once you are done running your system, the pump is turned off, you still have some level of push through flow, you can just simply turn an isolation valve off to prevent any flow rate into the system. Typically, there still is a little bit of a lag there, because you want to make sure the pump is off before the isolation valve is closed, because you don't want to cause any damage to the pump. So if you turn the pump off, there still can be several minutes of push through flow that flows past the pump until that isolation valve fully isolates the system. Now, it does limit the amount of waste you have, but like I said, you're still going to get a few minutes of waste, and even a few minutes of waste can be hundreds of dollars depending on the level of push through flow or pump slip that you're going to see. The biggest risk here is if you just have isolation valves in the system, if the control loop is not tuned correctly, or if there is any damage or any miscommunication in isolating those valves, what you really want to avoid is isolating the pump before the pump is off, because you can cause significant damage to the pump if that happens. So there is risk there. Additionally, you may see water hammer or shocks from isolation valves being closed too quickly that can all lead to either damaging the pump or then creating those pulsations in the system, which can lead to disrupting the resin of the column. So while this is an effective solution for limiting the amount of waste you're going to see, there's still some risk there to the actual damage of the pump. These pumps are very expensive in a sanitary process. So there are better ways to reduce the pump slip and also get more use out of your pump. And this is the key topic that we're going to talk about today, is the best way to really reduce pump slip in these types of applications is a high precision back pressure regulator that allows the pump to slowly turn off and limit or eliminate any sort of push through flow by having a set pressure that is equal to that net positive head pressure. So basically it cancels out that positive head pressure by setting that back pressure regulator to close right at that same level. So when the pump is turned off, the back pressure regulator closes off and eliminates any sort of push through flow. But then also, because it is only counteracting that net positive head pressure, once the pump turns on again, you do not need to make sure you open a isolation valve. That pump can simply turn on and it will overcome that set pressure of the back pressure regulator and immediately start working and flowing media into the column. What this also will allow is that pump is now able to run at much lower RPMs and much lower flow rates, because the back pressure is being held constant, and the pump is the back pressure regulator is effectively canceling out any of that net positive head pressure. So you do not need to limit the pump's ability to run at lower volumes. So here is just an example of what this system looks like, we ran a few tests in our lab. And so this orange line right here is the pump suction head pressure. So this is simulating a 7-foot elevation gain on buffers, which equates to about 3 psi net positive head pressure. So just having your volume of buffer one floor above will generate about 3 psi. Now, 7 feet is a very small distance. In actuality, a lot of these are stored much higher, but for the sake of this example, 7 feet of elevation, 3 psi head pressure, and this means that even when the pump is off, so the pump is not pumping at all. No, even at just standard at the standard application, there will always be just under 2 or just over 2 liters per minute of flow, because that positive head pressure is pushing through that pump and always generating that level of flow. And you can see the flow here in the gray. So from seconds 0 to 0.5, you have a constant flow rate of about 2.6 liters per minute. And this line right here in blue is the set pressure of the Equilibar back pressure regulator. So as soon as that the set pressure is turned on, so the back pressure regulator is air loaded and the valve seals off in about 1.5 seconds, so 0.5 seconds to just over 2 seconds, that flow is reduced to 0. So the push through flow is eliminated because that net positive head pressure is counteracted. You'll see there's still that head pressure that exists, but it is effectively a one-to-one cancel out to eliminate any sort of push through flow. And also what this means is once that pump turns on, it will, since the set pressure of the Equilibar remains constant, that pump will be able to overcome that set pressure very slightly and be able to start pushing fluid through the system without having to worry about the positive head pressure overwhelming the pump. So in another way to look at this, because a pump can only operate over that net positive head pressure, so we have 2 systems here. One is 7 feet of head pressure, or 7 feet of elevation. The second flow rate is about 10 feet of elevation. So a 3 psi net positive head pressure and about 7 psi of net positive head pressure. And what this is showing is down here, the flow rate. This gray area represents the uncontrollable area. So since you have 3 psi of head pressure in this initial system, you can only start controlling above that, which means the minimum flow rate you are going to be able to achieve is about 4 liters per minute. So after that, you can start controlling the pump and pump and have an effective control rate of 4 all the way to the high range of the pump. So 4 to 60, you have really good control. But if you need lower control than that, if you want to really fine gradient elution at lower volumes, there is no control that you're able to that is able to be achieved at this lower level because that positive head pressure. So like I said, that gray area is a known volume. Most pump manufacturers will even limit the rangeability of their pumps to about 20 to 30% above the low end. So if you're able to run from 10 to 100 RPM, they'll mention try to stay around the 20 or 30 range, just to make sure you counteract that positive head pressure because you can't get control on that low end. When you have that high precision back pressure regulator and you're able to completely counteract that net positive head pressure, you're effectively changing that y-axis and allowing that pump to work at the very low end, since it doesn't have to worry about that positive head pressure anymore. So this is the same curves and the same different options, but now you have that gray area has been shifted down, so you're able to accurately control at much lower flow rates of 1 to 2 single-digit liter per minute. And we have seen in our lab that we can control pumps down to single-digit RPM and getting very fine control at that low end because that net positive head pressure is completely counteracted by that set pressure of the Equilibar. So moving into what this product is, how it works, and why it can be so effective in this application. So this is a sanitary back pressure regulator. It is air loaded, so a 1-to-1 air load, and it works by having a 1-to-1 air load of the set pressure to the back pressure. So unlike some standard back pressure regulators or control valves that most people are used to seeing, this valve does not operate with a singular plug and orifice that moves up and down by either an air load or a spring. The control mechanism of this valve is this diaphragm right here and the air load on top. So instead of the media having to push up on a plug or a spring to then affect the flow rate or the pressure, the media is in a direct contact with a diaphragm that is a force balancing between that set pressure. So as the media comes in, if it's a small change in back pressure, so if this set pressure is set to 5 psi, as soon as the pressure of the system gets just above 5 psi, so 5.001 psi, that diaphragm is going to start to move out of the way and allow the smallest amount of media to relieve out of the valve. And if it is a much higher change, so if you need a much higher flow rate, it will move the entire diaphragm out of the way and engage in the multitude of orifices that it has here. So a very high rangeability and a very high responsive time, since the only thing that is moving is this thin diaphragm, rather than having to overcome spring tension and hysteresis of the springs, or even moving a plug up and down versus this design here. So adjusting the pilot pressure changes the equilibrium set point. As the inlet pressure falls, so as the back pressure of the system goes down, the valve will close completely, and that's where you see that elimination of your push-through flow. And if that inlet pressure increases, so once that pump turns on, the valve will then open. So you don't have any risk of damaging any pump or pump components. The valve will move in response to your system exactly how you need it to. One of the other things that is very critical to chromatography is limiting the amount of pulsations. So pumps in general are pulsation creators, right? So even if you have a very high-end pump that has minimal pulsations, just due to the fluid dynamics, there is pulsations that occur. And since this valve operates by having media flow through and basically be sandwiched between two separate diaphragms, it has pulsation dampening properties. One of the design features that this has is this crush pad right here, which was specially designed to limit the pulsations even further. And in the standard configuration, these pulsations are reduced about 25% of pulsation amplitude in the trials that we have conducted. So not only do you have this fast response time and elimination of push-through flow, you are also able to help reduce the pulsations flowing then into the column. And as I said, pulsations can affect the resin, which ultimately affects the separation process and the yield you get out of the column. So it is very important that pulsations are reduced. Because this valve has multiple orifices instead of just one, you have a high rangeability of this valve with an effective turn down of about 10,000 to 1, which means this valve is accurately able to control the back pressure through a large flow range. And in just this example here, this is a 3/4 inch FDO valve. It can accurately control back pressure, whether you're flowing 0.001 liters per minute all the way up to 1 or higher liters per minute. So as you're trying to get a very tight gradient elution and you need very low flow rates, or as it shifts to very high flow rates, depending on how your buffers are blending, this valve is able to work in a wide range of flow rates. So be able to hit whatever needs you have in terms of hitting those buffer blending targets. These can be controlled by either a manual or electronic pilot. So if you want to set the set pressure to just have a static counteraction of that net positive head pressure. So if the net positive head pressure is always 5 psi, you can have a manual pressure regulator controlling that pilot pressure, so that back pressure is always controlled at 5 psi. Or if your pressure changes over time, so as your tank gets lower and lower and that pressure changes, this can also be controlled by an electronic pilot, which feeds into a pressure sensor that adjusts the set pressure so it can respond in real time to the actual net positive suction pressure of your system. And then just some fundamentals, these valves are fully drainable. We know how important sanitary requirements are in this process. These valves are fully drainable. In the orientation of downflow, or sorry, with the inlet facing down, the valve is designed to have a channel here where all the flow will fully drain just by gravity. If you do need to install it in different orientations, the valve can be installed in any orientation with the use of an air blow to have it fully drained and fully sanitary. Very easy maintenance because there are no moving parts. You have the 2 diaphragms here and the crush pad, so these valves are tested to work for a very long time, and you don't have to worry about lots of parts when you compare it to, say, a control valve, which has a lot more moving parts that can either break or need replaced over time. This valve is meant to operate for a very long time and maintain all of those sanitary properties. And then just to sum up, we have worked with a lot of customers in this process because it is very prevalent through the biopharma and pharma markets. Chromatography is a very important process, especially into markets like oligonucleotides, which are rapidly growing and have their own challenges. And push-through flow is a big waste on a lot of these applications. So eliminating this waste helps the process become a lot more cost effective, but more importantly, it helps the pump be able to control at a much higher level or a much more precise level, and to ultimately improve the yield and the separation process to have a better product at a higher quantity through the overall system. So these valves are come all the way from 1/4 inch all the way up to 3 inch, but all of them have that 10,000 to 1 turn down to work through the entire flow rate range of your process. So that is all I have today. I want to thank you all for taking the time, and Andrew, thank you for setting this up. Please let me know if you have any questions.
Yeah, thank you, Megan. We've got a couple of good questions that came through the chat while we were presenting. The first one here, if you don't mind answering this, is if you have a high enough head pressure, would you need a pump, or could you just use a back pressure regulator to control flow?
Yeah, that is a great question. If you do have a high enough head pressure that is consistent, we have had customers use just a back pressure regulator to control that flow. If you have questions on getting into more detail on this, we'd be happy to talk to you about it and use more of a pressure-driven flow system. And yes, you can eliminate the pump in certain situations, which can be a big cost savings in this process.
Okay, wonderful. Next up, got somebody that asked, what is the recommended control on the pilot pressure of the Equilibar? What is recommended, for control on the pilot pressure of the Equilibar?
Great question. So if you have a static head set pressure that you want to maintain, you can use a simple, cost-effective manual regulator, like a Bellafram type regulator. Or if you want a more precise control, you can use a standard or a electronic pilot, and there are many different options for that. Depending on what your process is. But our engineers are available to take your process conditions, and depending on the turn down speed you need and the overall changes that you're making, I recommend the right product for you.
Okay, wonderful. Looks like we've got one more here. Last question is, what effect does pulsation have on the system for Chroma?
Yeah, great. So Pulsation on chromatography systems, like I said, it really can disrupt the overall yield of that column. And that is basically as you have pressure pulsations going into the column, those resins are very tightly packed and they are very highly engineered. So if you have pulsations going into the column, even if your control system doesn't pick up on them, they are disrupting that matrix of those resins. And when you get into applications like oligonucleotides, which are creating long chain proteins in the column itself, if you have pulsations, you can actually break apart those proteins that you are trying to create. So even if it is not very evident in your system, any pump is going to create those pulsations, which is ultimately going to reduce the yield that you're getting out of the column. So by just eliminating pulsations, you should be seeing an increase in yield and an increase in products that you're able to pull out of your column.
Okay, thank you for that. I think with that, I don't see any more questions coming through. So with that, I'll thank everyone for attending the webinar and thank Megan for her time. We appreciate it, everyone. This will be posted up on our website for viewing at a later time if you want to review the webinar. Thank you for everyone for attending.
All right, thank you.